Okay, so welcome back for our last talk of the morning. And it's our pleasure to have Thomas Pochart telling us about Haag-Ruelle scattering theory and the single particle problem in the Wightman framework.
Right.
Thank you.
Okay, so first let me warmly thank again the organizers for letting me speak here. I think it's a very nice place to talk about this because Ruelle was a teacher here for a very long time. He was a full professor. So I think there's a bit of beauty in the fact that this talk occurs in this room.
And you can meet him in concert with us.
Oh, I should have invited him. So what I'm going to say is mostly based on two papers that are to appear. This one, it's 2603, but I think it's not too hopeful. Really, it's going to be 2603 and 26XX, depending on the moment the cluster decides to work again at Polytechnique. So first, let me give you an overview of what's to come. So my plan with this overview is essentially to tell you the entirety of what is to come in this talk, so that if you decouple after 5 minutes, you still have all the take-home messages, and then I will proceed with the actual talk. So what are the Wightman axioms? The basic idea is to answer the question, by the way, what's a quantum field, and to answer that question in mathematical fashion. Essentially, I'm going to tell you that you have some Hilbert space that has a vacuum, and on this Hilbert space, you have quantum fields, and these quantum fields are operator-valued distributions. So you essentially, instead of taking those functions of x, you take functions of other functions f that are test functions. And I'm going to assume, you'll see why, some spectrum with the vacuum, one particle space, and all the rest with some gaps. And from there, I will tell you about the single particle problem, which is the following. So let's say you have a field, phi of x. Of course, I will keep using notation abuse and call my distribution phi of x. So you should imagine that this thing lives in an integral against some test function. And I know that phi of x creates states that have non-zero overlap with my single particle states. So ket p is a single particle. Bra p is a single particle state. And the question is, how do you create a corresponding single particle creation and annihilation operator? It's not that obvious to do because you might not be in a free field. Actually, if you're doing something interesting, you are in a not free field. And my first take-home message is that you will not be able to both localize phi in position space and momentum space to solve that problem. So some sort of Heisenberg indeterminacy in these fields. From there, we will move to Haag-Ruelle scattering theory, so the other part of the title of this talk and the mention of Mr. Ruelle. And the question I like to raise is, does there exist an S matrix in a very general Wightman field theory? And to do this, we will show that the answer is yes, and we will show it constructively, that is by building this S matrix, essentially by using the solution that was devised to the single particle problem to create in and out states. And we'll show that these in and out states have all the nice properties you might think of. In doing so, we will discuss a bit the implications of being in a dimension greater than 4 or just any dimension when you do this sort of games, which is a bit of an upgrade as compared to the original work by Ruelle, because Ruelle was only concerned about d equals 4. And then my second take-home message would be that if you give me a Wightman quantum field theory, then it naturally features an S matrix, and this S matrix, more importantly, is compatible with LSD reduction, because existence is good, but computability is better. And then finally, I will discuss a bit quantum field theory in ADS, so much more recent developments. And my take-home message would essentially be that this Haag-Ruelle construction is not some funny thing from the past, but it can also give us a lot of knowledge for the future in axiomatic quantum field theory, and more generally, quantum field theory. So that was an introduction to the talk, and now let me proceed to explain you what is axiomatic quantum field theory in a nutshell. So together we will work through the Wightman axioms. I will try to have this presentation, which is on a technical subject, to be as little technical as possible, so that you can really see what are the take-home message, what is the logic at play, and then if you want to go further down in these ideas, well, you can just read the papers. So the goal, as I said, is to find minimal requirements that will mathematically define what a quantum field theory is. I put the T in between parentheses because it will really be about answering the question, what is a quantum field? And so let's walk a bit through the logic. Well, what do I want if I have quantum field theory? Well, it's in the name, I want it to be quantum. And in particular, that's going to be my axiom W0. The numbering of the axioms is like, it's arbitrary, okay? Not all authors have the same axiom numbering. I picked one that served my purpose for this talk. So my axiom W0 will be that, well, I have quantum physics, and in particular, according to von Neumann, I have at disposal some Hilbert space. And in this Hilbert space, the states, the physical states, they are the unitracks. And further, my Hilbert space is separable. So now, you know, when you start the masters and you're told, like the very first time, what quantum field theory is about, you're essentially told something like quantum field theory is the daughter of quantum mechanics and special relativity. And because of that, it is natural to ensure that you are compatible with special relativity, and in particular with the Pochart group. So everything I'm going to say up until the ADS part will take place in flat Minkowski space. And we enforce this by saying that for Hilbert space should have some unitary representation of a Pochart group, so U, that depends on A and lambda, so the translation and the boost. And on top of that, you want the energy momentum spectrum to be in the forward Lacan. So essentially, you want P squared to be positive and P naught to be positive as well. Now that you have this, well, it's time to really go to a quantum field theoretic description of quantum field theoretic mindset, say. And the first thing I'm going to ask for is a vacuum. Because what you generally do in quantum field theory, again, if you think of CPhT 101, is you take a vacuum and then you act with operators, and this is going to be creating excitations or destroying excitations, and this is creating or annihilating a particle. And so I will ask for a vacuum, and we will ask for the vacuum to be unique. Okay, so this is a key part of the Wightman framework. I'll briefly discuss why later on, but we want this vacuum to be unique, and then of course it has to be Poincare invariant. Okay, so now let's move on and finally put our fields. So what is a field? Well, I'm going to define it as unbounded operator valued distributions. And we'll see that there's a few technical requirements that we want to have. So why operator valued distributions? Well, the idea is, first, you know that you want operators. So you know that you want something that is operator valued. And then you have hints that distributions rather than functions are a good framework. The first hint is that it already appears in commutation relations that you have Dirac delta, and Dirac delta is not a function, as you know, it's a distribution. Also, this is a very hand-wavy argument, but you know that generally fields can give you quote-unquote problems upon multiplying them. If you take some endpoint functions, for example, well, you know that, I don't know, if I take the endpoint function, the two-point function of a CPhT, if I put x minus y to 0, then I get something that blows up. That is somewhat reminiscent of what the sort of trouble that you might encounter with distributions. So that was a bit of a mathematical motivation. I would also like to emphasize that physically, it's not shocking to drop the idea that my field at this point exactly is well defined, because anyway, any measurement you do, you will do it not in a perfect point in spacetime, right? Any measuring apparatus has some resolution. And lastly, I would like to make a little comment, which is that I will touch on it quickly later, but even though the Wightman framework has still some challenges to overcome, we know that, for example, in D equals 2 and 3, there's been constructions of interacting Wightman quantum field theories where it was checked that the axioms perfectly hold. So, for example, you can have a look at Bloom and Jaffe for lambda phi 4 in D equals 3. I think that's the simplest one to look at for starters. And this is, to me at least, some hint that the Wightman framework is the correct framework. Okay, so now we are convinced that we want operator-valued distributions. Generally, it is that physical quantities, they're not bounded, you know? Like, if you just take, again, a very simple example, I take volume harmonic oscillator, which is a central notion in all these quantum field theory stories, you know that the energy spectrum is not bounded from above. So you want operators that are unbounded, so unbounded operators. Now, this comes with a mathematical subtlety, which is that generally unbounded operators, they are not defined on the entirety of the Hilbert space. They are defined on some subspace D, and we have to think a bit more to say some things about that D. The first thing I would like to comment is that D, okay, the subspace on which phi of f is defined, so phi being a field and f being some test function, it should be independent of the choice of phi and f. To argue for that, we are just going to say that naturally you want to be able to apply fields one after the other. So you want to be able to do something such as I take the vacuum, then I put phi 1 f1, then I put phi 2 f2, or vice versa. First I put phi 2 f2, then phi 1 f1, and so on. And the way to realize that is to have a domain that is the same for all phi's and all f's. And on top of that, you want the domain to be stable under the phi of f, so that you are sure that you can repeatedly apply your fields. Of course, as I said, you are going to act on the vacuum, so you want the vacuum to be in D. And the last thing I'm going to ask for is that D is dense in H. Sometimes, if you look at pedagogical expositions of the Wightman axioms, some people claim that D being dense in H has to do with cyclicity of the vacuum. I disagree with that statement. The mathematical reason why I want D to be dense in H is that I also want to be able to take adjoints, so Hermitian conjugate of my fields. And mathematically, this is done through the Riesz theorem. And for this process to be well-defined and produce one single answer, for the dagger to be single-valued, if you want, you need D to be dense in H because you want the orthogonal to D to be the implicit or singleton zero as well.
Is H still separable?
Yeah.
It will be.
Yes. Yeah, I will always take it separately. Okay, so now we are very happy. We know what a field is. But again, we want all this story to be compatible with special relativity. So we ask for it the natural way. That is, we want to have Poincare covariance. And of course, we want causality. So in this statement, I'm writing everything as if I'm dealing with functions. Of course, it is again a notation of use. And if you want to be rigorous, you should really uplift this statement to test functions whose support has some separation, some spatial separation, and this will give you the commutation. So you take the pointwise statement and you average it over some regions of space that have the correct separation. And lastly, here comes cyclicity of the vacuum, which is that the span, so the set that I can get by getting linear combinations of the vacuum and some finite product of fields that is acted on the vacuum. If I take the closure of that, I recover the entirety of H. Meaning H is not too big, so I access all the physics.
We know this is not true, right? In general.
Okay. Let me say that thing. In general, axiomatizing quantum field theory is really a very big endeavor. It is very hard to axiomatize the full of quantum field theory. So actually what we do with the Wightman axioms is not really to define what a quantum field theory is in general, but rather to say, let's pick a subset of quantum field theories in which we make a trade-off, which is, okay, we're not going to cover the entirety of quantum field theories, but we're going to try to cover something that's as big as possible using axioms that are as manageable as possible and as amenable as possible to mathematical development. For example, it's very nice because it can like put you on a solid footing to discuss analyticity properties of scattering amplitudes, for example, and the connection with this seminar series as well. It can also help you produce no-go theorems. It can put some rigorous mathematical footing on some bootstrap techniques. But I agree with you. We were not going to cover everything. Actually, it's part of the aim of this slide to discuss that we do not cover everything indeed with the Wightman axioms.
But to make it sound a little bit more positive, for the purposes of considering scattering processes, you can just define your H to be what's on the left-hand side of that equation.
Yeah. Yes.
Maybe there are some other operators, maybe there is a bigger H, but you just call H this, and it's enough for the purpose.
Yeah, yes, thanks very much.
To say that it's the full Hilbert space. It's just a Hilbert space in which you can perfectly work for all you want.
Great. Yeah, thank you very much. Yeah. So I have this little meme slide. I actually used that slide in some other talk that was much less formal, but I thought it conveys quite well the idea I want to give regarding the status of Wightman quantum field. So there are things that work extremely well. We have got this thing called the Wightman reconstruction theorem. Very simply put, you've seen that we put a special emphasis on that, so vacuum expectation values, because you have a single vacuum and such. And the Wightman reconstruction theorem is telling you, well, if you give me a collection of Wightman functions, so these distributions that you obtain by taking your fields and taking the VEF, then I can reconstruct the Wightman quantum field theory that corresponds to them. So it really is a sort of bijective between this vocabulary of fields and this vocabulary of Wightman functions. So that is very nice. You can derive the CPhT theorem, you can derive spin statistics, you can derive the non-existence of faster than light signals. We can do Haag-Ruelle Haag-Ruelle theory, which is, well, the remainder of the talk, so this I will explain later. And, just for mentioning the millennium problem so that I have this side quest unlocked in my life, it is mathematically very sound. And actually, if you look at the way the Clay Institute posed the Young-Mills problem, they say in a framework such as the one of Wightman and Streeter or equivalent, blah, blah, blah. So even mathematicians are very convinced that this is a very steady, steady base on which you might build some quantum field theory. Then, it might get a bit more subtle sometimes. So first, it's not so easy to use, right? It's much easier to deal with functions than dealing with distributions. And then there's the question, by the way, are these satisfied? So for example, as I told you in D equal 2 and 3, we have interacting examples that have been found. In particular, I can have a look at this Glimm-Yaffe construction for lambda phi 4. In D equals 4, so far as I know, and from what I've checked, last check being yesterday evening, so I think it's still true, we don't know interacting examples in D equal 4. So that remains an open question.
Thomas,
yeah.
For example, like lambda phi 4, why? I mean, do you know why it's not possible to reconstruct it in like D equals 4 with the Wightman axioms? I just said a random.
Okay, so the idea of the construction in D equals 3 of Glimm-Yaffe is you put things on a lattice and then you take a continuum limit. And then you have to be rigorous when you do that. And essentially, if you work out the arguments, you realize that starting at after D equals 3, you're not going to get enough convergence to have a well-defined answer out of that process. That's essentially the problems that
No, but we can answer more physically. These axioms they mathematically define the notion of UV completeness. You know that lambda phi to the 4th is not UV complete.
Yeah.
Because of the lambda fold. Not work.
Yeah. Okay. I see. Thank you.
Thank you. Gauge theory compatibility is even further down the line in terms of complexity. And then I would like to just comment briefly on EFTs and thermal QFTs, because I think these are the simplest examples where you can see that there is no hope that Wightman quantum field theory covers the entirety of quantum field theory. For example, why will thermal quantum field theory not fit in that framework? It is a framework about vacuum expectation values, not thermal expectation values. So of course, because the emphasis is not put on the correct quantity, they are not going to emerge. When I talk about EFTs, I really mean theories that are defined as EFTs, and then you might not know what's further down the line energetically. And you've seen that I never introduced any index in the phi saying, the phi depend on some parameter, lambda, whatever you want. So just for that, it is a very hand-wavy and rough way of telling you that no, the Wightman axioms will not cover everything. But again, that's fine for purposes, or at least the purpose of this talk, which really is about scattering.
So,
yeah.
When you say gauge theory compatibility, you mean showing that gauge theories exist within this algorithm?
Yeah, meaning I can take a gauge theory and say, okay, this is my gauge theory, that's all the features I expect physically, all the things that we physicists do with it, and yet it satisfies all the Wightman axioms.
And in 2D, have people proven it like Gross-Neveu or something that we know that is a toy model of the CP1 model or something that is gapped along distances. But it's really a theory of scalar fields at the end of the day, so probably one can show. Is this shown to exist in 2D? So before trying to do gauge theories, there's
I'm not sure. I don't know. I'm just gonna say I don't know. I think it's the best thing to say. Also, you mentioned scalars, so let me just say that for the entirety of the talk, I will be dealing with real scalars in order to not clutter the board with indices everywhere. But of course, everything I say can be uplifted with the proper algebra to spinning terms. So now let's go to a bit of setup, where I will review a few things. I'll be rather quick because I guess it's things that you all know. But just to introduce notations. So I will look at d-1 plus 1 dimensional Minkowski's flat space. I will use the mostly minus metric. That's the only political statement of the entirety of the talk. Fourier transforms, I'm not going to bother with tilde, hats, and these sort of things. So I will just write the correct variable, and then we guess we get from the variable which is which. Let me just recall you that if I look at a massive real free field, so if you look at the massive real free field, it obeys the Klein-Gordon equation. You can solve it in momentum space because you know it's linear, so you just Fourier transform. You get creation and annihilation operators that have this expression. Noticeably, when you are free, it's independent of the time. So for all time, this right-hand side gives you the same answer. So you can just call it A of P or A dagger of P. And then the Hilbert space is, roughly speaking, this Fock space. I'm saying it's roughly speaking because it's not really linear combinations, because you need some continuous linear combinations or wave packets, and that's smearing. So that's again a hint that distributions are a good language for this sort of stories. And so if I do the distributional version of that story, I essentially end up with these formulas. Also, dp with the d at the bottoms means over 2 pi to the d. So that's a cheap alternative to setting 2 pi equals 1, which I will use throughout the entirety of the talk. And hopefully I did not forget the lower d anywhere. Hopefully. Okay, so now let me just give a few reminders about truncated Wightman functions. So essentially, they're what cumulants are to moments. Okay, so you define them the usual way in physics. That is recursively through this formula. You can also invert this formula. You will have essentially a minus y and some counting factor. That's a factor that will appear. So you know, like the 1-point function, they are 0. The 2-point function, they're the same. The 3-point function, they're the same. And starting from the 4-point function onwards, you have to really pay attention, and you have to remove some 2-point function to the 4-point function, and so on and so forth.
So is it the connected?
Yes, exactly. That's the connected part. We will call it the truncated part, and sometimes we also call it the connected part because I'm not self-consistent with that. Just notice that in the Gaussian case, of course, by very definition, these WTs, so these connected functions, truncated functions, they vanish. So another ingredient I'm going to need for my discussion further down the road is cluster decomposition. So physically, it is the idea that if I go at very large spatial separation, you'll agree that my experiments should be uncorrelated. And the function heuristic statement is you should have this sort of product decomposition. So yeah, it's really a heuristic. I'm not yet telling you about distributions, just telling you that, well, I take some endpoint function, I separate it into groups. One group I send spatially to infinity, and then I should get a product because there's independence in the measurement. If I want to make a proper distributional statement in truncated Wightman functions, essentially I'm telling you that, so again, I take some n+1 point function, and I'm just going for the sake of the argument to look at what happens if I set k equals 1 in that expression. And the claim is that this goes to 0 as a special meaning. The special meaning is belonging to the Schwartz class, which is the best way mathematically you'd expect things to go to 0. And indeed, if I take my truncated Wightman function and I smear it against some test function, I will recover some Schwartz function in the A's that I've introduced. Okay, so it indeed goes to 0 in the spatial variables. This statement is valid for compact momentum support, that is non-space-like separated operators as well. That's a remark for now. We'll see later why this remark plays a role. Also, just to do a bit of advertisement for the paper, this cluster decomposition I just mentioned, if you looked at the literature so far, even the historical literature, you never had a full mathematical proof. We do have one. So I think we've got that for us. Completely another ingredient I'm going to need. That's the last technical ingredient I will need, and we will go on to do proper physics and go back on track with the main story I'm telling you, is about the classical solutions to the Klein-Gordon equation. Can I remove this black square? I have no idea. I don't really know.
There's moving down.
Maybe not.
No, but because I don't have it on my screen, and it is on this screen, so I'm a bit surprised.
There's no good way. I'm
So we
sorry.
know
Very important equation.
Yeah.
Okay, it's
I'm sorry.
Yeah.
We tried many times.
okay. Let's not worry then. I maintain that Skype was better than Zoom then, but we can resume this argument offline. So you just know that if I take Klein-Gordon, classical Klein-Gordon, you have a uniform decay everywhere that take this form. You can, if you derive it, it's not very hard. Also, you can just argue it with some acoustic type argument. By acoustic, I mean you look at the energy density and you just say it has to be conserved in essentially surfaces of increasing time. I would like to mention something that will be very important for the rest of the talk, which is velocity cones. So I'm going to define a velocity cone for some function f that has some compact support in momentum p. So this should be p vector. This is a bold p that I took from the paper. And I will define the velocity cones as the set of lines that I obtain by taking some momentum p in the support, and I complete it with EP, the corresponding energy, and I take alpha to be any real number. Okay, so it really is a cone. And a comment I would make is that this definition I gave you in momentum space, but of course it is an angular definition. It defines me a set of angles on the unit sphere. So I can take the same cones in the position space and it makes perfect sense. And interestingly, outside the velocity cone, you have a much better decay, because if I take any compactum of the Euclidean unit sphere that does not hit the velocity cone, I have this power law, which interestingly is valid for any power in T. Okay, so this you can show as well. It's playing some mathematical games. The Soviets were very good at that, so I think Bogolyubov for a very efficient derivation of that bound. And the rest of that talk, I will describe the solutions of Klein-Gordon equation that I just discussed, which have smooth initial data that is completely supported in momentum space. So this, I will just call it script K, okay, for the sake of having light notation. Okay, so let's go on to the single particle problem. So what is the single particle problem? In everything I do, again, I will assume that I have a single real scalar field, and then you can uplift that to the spinning quantities of your choice. So the question that we have is, how do we reach the associated single particle subspace using phi of x, which is some very natural question, because when you're a kid, in kindergarten, introduced to quantum field theory, you're being taught that fields enable you to start from the vacuum and hit the single particle subspace, and then you can do it again, and so on and so forth. So for a free theory, it's pretty simple, right? You just apply phi of x to the vacuum, and then essentially you will recover this. Why? Because phi of p has this content, and it already features a delta distribution that will localize you on the correct mass shell. However, for an interacting theory, it's much more complicated. It's much more complicated because your field phi might have momentum content outside H1. And actually, my claim is, if you take a test function that has compact support in position space, so you localize your field in the position space, it will delocalize in momentum space out of properties of the Fourier transform, and you are bound to hit the threshold after which, for example, multi-particle starts. So that's some sort, again, of Heisenberg indeterminacy. And to solve that, we will rely on this technical assumption that was first proposed by Haag and Ruelle about 50 years ago, which is to say, okay, let's assume that our theory has this double gap mass spectrum. What you should really think is that we mean the theory decomposes in orthogonal subspaces, one that is one-dimensional, which is the vacuum subspace, one that is infinite dimensional, which is the single particle subspace of mass m, and the rest that start at some mass big M, capital M, that is greater than lowercase m. And the idea that we want to have is to select only the momentum content that belongs to H1. And to do so, we will use the fact that we have some leeway on the left and the right of lowercase m. In practice, what we mean is that when we smear against test functions in momentum space, we want our test function to have their support near m squared. When I say near in this slide, of course, I mean close enough so that it doesn't hit neither 0 nor all the junk that support capital M. And this enables me to define one particle creation and annihilation operators. So with this F that belong to this set D1 I've just introduced. And they are defined the same way as you define them in usual quantum field theory. Interestingly, because we are in an interacting field theory, of course, they depend on T. So again, here is my first take-home message. to solve a single particle problem, you have to localize in momentum space, and thus you cannot do so in position space. Not that this has some practical relevance if you're interested in studying scattering, because there's a variety of papers that do mathematical operations, such as, oh, we take a field and then we send it to spatial infinity, to the far past, the far future, and they do such procedure by essentially localizing it in position space. But then they also claim that if I act with this field that is localized in position space on the vacuum, I get a single particle state. Well,
can I ask a question?
Yes, sure.
So do you define this operator AT over M?
Yeah.
And you call it one particle creation operator?
Yes.
So can you explain in which sense it is a one particle creation?
Sure. So the idea is if I hit the vacuum with the creation operation, the creation operator that is just here, I will get some linear combination of vectors of my Hilbert space that all belong to the H1 subspace, so the subspace that is the middle red dot. Does that answer your question?
Yeah.
And only there?
And only there. That's the whole point of having this support that is located near M squared. Precisely because we have this leeway. Maybe I can do a little drawing that will make it more visual. So my drawing is the following. So this is mass squared. This is 0. This is n. This is all the junk. And what we want to do is to have a support that looks like this. Oh, there are supports. So in the end, I was using the convention that 2 equals 1. Okay, so this is what we want for our support. And so you see that because we hit 0 here and there, we will not encounter a vacuum contribution. And most importantly, we will not encounter any other matter contribution. That's why this technical assumption is necessary in this construction by Haag-Ruelle.
But you call it technical assumption, but it's not a technical assumption. It's
Yes,
a very natural physical assumption. It's always like that.
Yeah, so it's here I called it an essential assumption because it is in the essence of thing. I was trying to qualify this assumption. So
basically the width of this thing,
yeah,
kind of the 1 over that tells you how localized it is in position space, right? But if you didn't have like really compact support, that it had some tail that overlaps with the multi-particle stuff, maybe you could show that there's like exponentially small multi-particle contributions or something. So
yeah,
a big deal anyway.
Maybe I think you should be able to play this sort of games, but then it's much more involved because you don't have this rigorous statement of I am hitting the single particle space. You have a statement which is I am essentially hitting the single particle space, and then the other contributions are going to be neglectable later on. But then you need to be much more fine in the statements you make in terms of what sort of decay you have. So I agree, it is a very natural question to ask. But yeah, so the Haag-Ruelle construction is mostly concerned about getting a rigorous and strict statement, because then when it comes to defining an S matrix, which is like the end goal of this series, we really want to be able to say, okay, this is a one particle state. We will see in like the technical derivations that at some point I will be very happy to have one particle state and nothing gets inside it. Are we all on board so far? Yeah, okay, cool. Okay, so now let's reach the promised land and go to the flat space Haag-Ruelle construction. So I will first state your Ruelle's theorem in full fashion, and then we will go on to first give an intuitive argument as to why this is true in the context we have discussed so far. And after that, following a little auxiliary theorem, I will proceed to show you that the theorem indeed holds. So my assumptions are going to be the following. I'm going to take a collection of test functions that are in my D1 subspace. So again, D1 is having support like this. And I want them to have disjoint spatial support. So what do I call a disjoint support? It's the definition that is here. It is you take the support in the full space-time, and you look at the projection on the space axis or the space subspace of the space-time. And what that corresponds to is having disjoint velocity cones in the Klein-Gordon vocabulary I was discussing earlier. And under these assumptions, the Ruelle theorem states the following. So the first thing we have is a strong convergence of these states. So where I put some time t, I just act repeatedly with some creation or annihilation operator, the way I want on the vacuum, and I get some states, and I do get strong convergence. So in particular, that enables me to define states phi of in and out in a non-ambiguous way. These limit states, they do have free-field respective inner products, which is what you physically expect, right? So far, it is physically acceptable to call them in and out states. Interestingly, the convergence rate is faster than any power in 1/t. And then you have this, of course, the two things you'd physically expect, which are pretty straightforward to check once you've gone through the derivation, which is that they only depend on Fi is reduced to the mass shell. In other words, whatever the shape I put of the exact support, so long as it's not hitting the other scale, so the junk scale, let's call it, or the vacuum, I can put whatever I want. I'm going to get the same answer, which is very natural because there's no matter here. So it should not matter, no pun intended. And it's Lorentz frame independent, again, of course, because, well, we have built something that is spatial relativity compatible from the get-go. So if this was not Lorentz frame independent, then that means you made a mistake in the computation. But of course, the theorem has to be right. And interestingly enough, for d greater than 4, you can actually release the assumption that the velocity cones be disjoint.
Greater or equal?
Greater or equal, yeah, sorry. Yeah, greater or 4, 5, 6, and so on. So for d greater or equal than 4, you can release the assumption that the velocity cones are disjoint, and all the conclusions remain, but the third one. A little historical comment. So originally, Haag-Ruelle did all this construction in d equals 4 only. And so they did not have this discussion of whether velocity cones are disjoint and so on. It is more recently when we are working on this that we came to this conclusion that we need disjoint velocity cones if we want something that is dimension agnostic. So something that I would say is like really a property deep down of all quantum field theories in the Wightman sense. And then for practical purposes, if you want to be able to cover all the velocity options, then you need d to be greater than 4. So interestingly enough, we realized that d equals 4 is the richer case.
So I presume that the convergence rate becomes a power law.
Yes,
okay.
And we will see
that. Okay.
We will see that as well. That's a very good presumption. Take-home message number 2, we've hit the second take-home message, which is that it literally defines me an S matrix, right? Because now that I have this wonderful in and out state, I can just take the overlap, and that's how you define an S matrix. So let me first argue. Yeah.
Can you explain physically? So you are dealing with the massive theory.
Yeah.
Or, but can you explain physically why you need the disjoint cone? The disjoint cone means physically you don't want particles to move along the same direction.
Yeah, exactly. Yeah.
So can you explain physically why it's an important assumption, even though you have a massive theory?
The idea is that if we think in momentum space, no, rather than position space, because again, these cones are valid in both momentum and position space, you want the cones not to overlap, to not have to take into account content that is along the same direction, because then you'd have some interaction in that direction. Whereas if you separate them, you'll be able to use that decay to, you'll have this decay that enables you to be sure that where you go further away, for example, you have non-interacting in and out states. It's not so obvious to get the point 2 and the point 1 at the same time, actually.
Okay, then the argument you just gave doesn't depend on the number of dimensions. Why is it that in d equal 2 dimensions you don't want to have interactions happening in d equal 4 dimensions? It's not a big deal.
Okay, I'm going to. I will come back on that. It's a very good question. I'll come back on it in one slide, but to not leave you like this, I can still start to give a hint of what my answer will be. We had this power law decay everywhere in the Klein-Gordon discussion. And it's a very nice decay, but it's a decay that does depend on the dimension. And generally, when you want things to be well-defined, typically, if I want some state to evolve, what you can do is say, okay, I take phi of 0, and then I add the integral from 0 to t of the derivative. And you want this derivative to decay fast enough for the integral from 0 to infinity to essentially be well-defined. That's how you would proceed to define phi in and phi out. And if you have any k that you want in the Klein-Gordon decay, then you're safe, essentially. That's my take-home message, that these Klein-Gordon properties will essentially boil down to properties of these, the test functions f that we have. However, if we go to small enough dimension, this decay might not be enough. And we will see that there is some reflection of this Klein-Gordon decay in properties of truncated Wightman correlators. And this is essentially this reflection that will answer your question as to why in d equals 2 and 3, this decay is not enough.
With equal 1, because your case, you also covered equal 1, right?
Yeah. Okay, so let's consider some. So I'm going to first start by some intuitive derivation. I called it the intuitive derivation of quote unquote 1 and 2. So why quote unquote 1? Because 1 is a statement about strong convergence, and I'm not going to even try arguing of strong convergence. I'm going to try arguing of some very weak form of convergence. But again, that's just an intuitive derivation. So let me consider some VEV, okay, of some of my 80s or 80 dagger. I will only call them 80s, but you should really think that it's 80 or 80 dagger of some of my 80s with my Fs that are in my nice subset D1. And a little computation can show you that we can write this in this way always. So starting from the definition in the integral, and you realize that the chi that appears here, literally is a solution to the Klein-Gordon equation with a momentum that has compact spatial support. So literally the velocity cone setting that I was discussing earlier. And so essentially, if I do this and I expand in a truncated Wightman functions, I essentially get a sum of product of, okay, here I call them connected and not truncated. But essentially that's a connected expansion. And now let me make a few approximations. Again, keep in mind that this is not mathematically a proof. It's me shaking my hands and hoping that the audience will believe me. First approximation I'm going to say is that, well, you know, the decay is very fast outside of these velocity cones, and inside these velocity cones, I just have a power law with a fixed exponent. So first, let's say that these integrals I'm going to restrict only to the velocity cones intersected with the slice of time t, okay? So if I were to give you a drawing, this is velocity cone, okay? This is some time t. And this is CF of t, okay? And the second approximation I'm going to say is that, well, there is cluster decomposition. So if this CF of t were to not overlap, cluster decomposition will also give me fantastically fast decay. So let's also say that we will only be looking at the region where all these CF overlap. This region might be the empty set, but it might not be as well. So now, this region here, okay, at most, the size scale as the time to the power d minus 1, you agree? It's essentially an acoustic argument in classical mechanics. But the decay of my k points goes like t over minus d to the 1/2 over 2 times k, because I have k of them. So if you compare both, you see that only k equals to survives. So that's exactly the free fit behavior, right? If I expand in connected parts and I only get the 2 points. That's essentially an argument as to why things go well. What I really mean is I got these terms, okay, and I'm integrating over some domain, and I'm making successful approximations to first say that this is integrated over the entirety of space-time. But hey, how about we just look at this slice here, because outside the decay is so fast regardless. Then I'm making a second approximation, which is, imagine I have 2 of them. Okay, let's call them drawing. Imagine I have 2 of them like this. You see that as time goes on, they will become more and more spatially separated. And I claim, and I will be more rigorous in that in a few minutes, I claim that actually this separation will be enough to make a play out of cluster decomposition and also get rid of these contributions.
Are you trying to say that all creation annihilations will be paired with some annihilation operators?
Essentially, yeah. Essentially, we only get
because
okay. So that's the claim. Again, it's really it's not an amazing proof. It is an argument of me shaking my hands and telling you that if I get decay at any power I want, then it's like 0. So in order to perform a complete derivation, I will need an auxiliary theorem that I will not prove. I will sketch you the proof. Proving it is essentially putting in play the proof of the sketch, but it would take quite some time and it's rather technical. So I thought that for a talk, we could like put that under the bag. And of course, I'll be happy to discuss it offline and ask your questions if you have. So my auxiliary theorem is, again, I take a collection of functions in my set D1, and I claim that if I look at this construction out of the functions, so you see that you have an extra phase, but this extra phase does not change the stages of being in D1 actually, and you integrate against some truncated expectation, truncated Wightman function, you get some power law decay. And to come back on your question, Slava, you see that here I have a fixed exponent, and this fixed exponent makes appear d-1, and this d-1 actually is essentially the same d-1 we had in the Clay-Gordon decay, so the acoustic d-1. And if furthermore the FIs, they have this joint spatial support, because that was the key assumption that we put at the beginning of Ruelle 2.0 theorem, then actually you can take any A. And the idea is that if it's literally the same thing, if now they have this joint spatial support, and by that they really mean that the intersection in total is 0, so the full intersection, then I can take any exponent, and the reason is, well, in the Klein-Gordon solutions as well, I can take any exponent. So how do you prove that? Well, the basic idea is that we are going to massage a bit that, that formula in order to make appear some solutions of my Klein-Gordon equations that have a support that is compact in momentum space, and some Schwartz function. So the idea really is you just massage that function and you recognize, oh, on the one hand, I have my Klein-Gordon solutions, kind of as expected, I would say. And on the other hand, we have cluster decomposition, which is a very strong statement about being in the Schwartz class. And then the idea is that now we have all these integrals, and we are literally going to play this game I just described of looking at what's inside and what's outside, except we are going to do it rigorously. So instead of saying what's outside the velocity cone is 0, we are going to separate the integrals, and we are going to essentially play inequalities games in order to get estimates. And then eventually we will take t to infinity, and we will get that indeed for t greater than 1, or to some constant that you can rescale, you get this estimate. Do you believe the auxiliary theorem? Again, it really is just restating the cluster decomposition and Klein-Gordon magical property. Okay, so now let's prove Ruelle's theorem. I will mostly focus on proving point 1. Point 2 is the same thing. Well, 3, 4, 5, you'll see that it's pretty straightforward once you've seen how to do point 1. And I will comment on point 6. So to do the strong convergence, we are going to say that we want to do the definition like this. So here, okay, I put plus infinity as the integral should be plus or minus infinity. That's a small typo. I'm only going to do the proof, say, with plus infinity, but since I have absolute values of t's everywhere, it literally is the same thing everywhere. So the goal now is to ensure that this is well defined. This is what we want to do, right? And to do so, we want the integral on the y to converge. If it doesn't converge, then too bad. It doesn't work. So now let's have a look at my phi of t. As I recall you, my phi of t is built by applying n of the a or a daggers on the vacuum. So if I look at what happens when I differentiate it, I'm going to get something like this with exactly one differential somewhere, or actually a sum of this sort of thing. This is, I think it's called the Leibniz rule. I'm just essentially saying that f times g and so on is f prime times g and f times g prime. Actually, we had a lot of discussion as to how to write that in the paper in order that it's very, very easy to understand. But I
didn't write, we use Leibniz rule. You said something.
No, I didn't buy this. But when I first read about this, I misunderstood the notation, and my fantastic advisor had to explain me, and then I was like, oh, okay. So that was just kindergarten. Oops. So now if I take two of them, then I literally take two of the derivatives, and then, okay, the expected, the game we expected. So we expand in truncated functions, so we get a sum of products of terms of that form, where there is at most two derivatives. Because you know you get the product, and then the two derivatives, they might end up in the same term or in different terms. Okay? And interestingly, regardless of whether you put a derivative or not, regardless of whether you put a dagger or not, at the end of the day, this thing is of the form, so these operators here, they're of the form some integral of some f that has, so you know the nice compact support, it is in D1, times some phase, okay, times s. So when I put that in the truncated expectation value, the auxiliary theorem applies. So I'm very happy. I'm very happy because essentially, now I just have to check that I have enough power law to decay. So we just have to pay attention about one thing. We assumed that the velocity cones were disjoint, but you assume that for the n functions that are in one of the bras of the ket. But now we put the bra with the corresponding ket. So actually they're pairwise identical. So we have to be a bit more careful. If I take a term that has k that's greater than 2 strictly, then there are 3 of them, and my cones are pairwise identical, otherwise they're disjoint. So there is at least 2 cones that are disjoint. So the full support, the full intersection is disjoint as well. So I can drop the auxiliary theorem. Now, if I put k equals 2, it's a bit more subtle. I might have a contribution with a product of k equals 2. So like the free fit behavior. But then at least one term in the product somewhere has to have one d over dt. And this d over dt, it cannot be in the middle. It will have to act either on the left or on the right on the vacuum. And this is time independent. So actually, I also get a 0 contribution out of this. For the free field inner product, it's exactly the same logic, except that now that I don't have the d over dt, the only term that survives are the products of 2 points. So that's exactly free field behavior. So you see that the auxiliary theorem, which is essentially restating the conclusion of the Klein-Gordon decays everywhere and the fact that they're better outside of velocity cones, plus cluster decomposition, leads us to a complete proof of the Ruelle statement, regardless of the dimension, the moment I can play with disjoint velocity. So as I said, 3, 4, and 5, it's literally analogous computations. For example, if you want to check that you do not depend on what you put exactly on like the leeway, where you just take 2 of them, you do the subtraction, and you look at what you get. So this, I'm not going to tell you much more about it. I would just like to make a comment about the validity of the previous points, and this will go back to Slava's question for d greater than 4. So you see that the moment I don't have the disjoint velocity cone, I am stuck with the original A, not choose any A of the auxiliary theorem, which means I am stuck with the power law decay at fixed power from Klein-Gordon. And well, it's this term. And so now you see that, for example, if I put d equals 3, then here I get 3 minus 1, that is 2. And so I get 1. But the problem is that the integral of 1 over t does not converge. So that's essentially why you get a non-convergence in d equals 2 and d equals 3. This is where this critical dimension comes from. If you were at 3 plus epsilon, you'd get the integral of dt over t times to the power of 1 plus epsilon, and by Riemann integration, that's enough. But not exactly for that one.
Doesn't the fact that you took a time derivative help?
I
mean, you absorb it in this f of p. But actually, you didn't take a time derivative.
So we did take a time derivative, though it doesn't help because the way we play your estimates is to say that this time derivative essentially, gets a term out of the phase, and then this term is absorbed in the f of p because it's not going to change where it vanishes. So unfortunately, we cannot, or at least we did not find a way to use this time derivative to snatch d equals 3, for example, along the way. D equals 2, physically, you'd expect that d equals 2 is special, but d equals 3 was a bit of a surprise for us.
If you fix the f just by dimensional analysis, shouldn't this converge better than the original thing?
Okay, I agree with your statements, but in practice, the road we have so far in the proof does not help us reaching the d equals 3 case. It was actually quite a surprise for us to realize that d equals 3 at this square. D equals 2 were not surprised, but d equals 3, it was surprising. That's the best I can tell you, unfortunately. And also, let me just mention that existence is good, but computability is better. And so all this is compatible with LSZ reduction for the time-ordered product, but also, fancier LSZ reductions if you know them. So retarded products, advanced products, these sort of things. Well, you can play these games with the S matrix we just defined, and it all works very well. In particular, it works very well if you just take, these non-overlapping velocities. So you can have LSZ in your d equals 2 or d equals 3 favorite case. So I think that's pretty good.
Can you explain? Maybe you don't have time. It's okay. I'll ask you.
Anyway, are you somewhere here saying that real proof in D equals 4 was not as complete as your new proof? D equals 4?
Okay, so then that will be the second political statement of the talk. Let's put it that way. I don't have like some eidetic memory of all the papers that I've read or that are in the world. The one thing I know for sure is that when Real argued for cluster decomposition in his original paper, or at least the first paper and main paper we read about the subject, he goes the following way. He says that he will prove that we are in the S class by only looking at radial behavior. And actually, you can find a counterexample to that. So I'm going to draw you the counterexample and not give you an analytical closed version. So counterexample, I'm going to draw the counterexample in 2D. So counterexample is the following. So this is so it's not space-time, it's really some counterexample. And I'm going to look at a curve that does like this. Okay, and the idea is that this curve I just draw you, it gets closer and closer and closer to the y-axis, but it never touches it. And so I always have some epsilon here. And now what I'm going to construct, and you can prove that you can construct something that way, a function that is completely smooth, and that is 1 on the curve, and that is 0 after epsilon over 2. So what happens is that this function is not Schwartz, because it's not going to 0 everywhere at infinity, because I can take a sequence of points where everywhere the function is 1. So along this curve, it's going to 1. However, if I take a radial direction, there are essentially 2 cases to consider. If I take everything but the upper y-axis, I will hit at most once the curve. So I wait a distance around epsilon over 2 because there's the angle. And then good, I have uniformly 0. Now, if I hit the y-axis, you have to be convinced that out of construction, we made it so that this function is always 0 on the y-axis. Because the leeway is epsilon, but we cut the non-zero behavior at epsilon over 2. And so this is a function that is indeed a radial, radially Schwartz if you want, because we hit exactly 0. So it's a decay that's faster than a after some scale, I have uniformly 0. And yet it's not overall going to 0, so it cannot be Schwartz by construction. I don't know if that, to what extent that was convincing. Maybe there are other papers where there are better discussions of this cluster decomposition, and now you prove it and everything. But so in the end, we just manually proved the cluster decomposition. All right. And we are on time for finishing the talk with some discussion about ADS space. So I'll be very brief on that. So just why should you be interested in form fit theory in ADS? It's not just some fancy thing of me telling you, hey, look, we did something in flat space. How about we do it in some other space and let's take ADS because it's not too hard. The main reason is that ADS is a wonderful tool if you want to study confinement. Generally, when you have strong coupling, your main issues are tied to IR physics. And the natural solution is to put your theory in a box. Then you want a nice box. And what is a very nice box? It is a very symmetric one. And a very symmetric box is ADS. So that's one of the main reasons why you want to study ADS. Also, let me emphasize that ADS has infinite volume even at finite radius. So you can find phase transitions, symmetry breaking, and all the sort of interesting physics you want to have a look at. This theory, it has access to the conformal toolbox because on the boundary of ADS lives a conformal symmetry. So this is very nice. Also, it gives you access to the conformal bootstrap and all the wonderful tools that have been developed by including Slava the last 15 years. So that is very nice. And lastly, it is connected to the flat space. So you see it right away from the metric. But I would like to emphasize that you can have quite some mathematical control over how the flat space limit is taken. You can have a look at papers by Bart van Ries and Chang Zhao about that, where they explain you essentially, and Joao Pinedo and this sort of people, where they essentially explain you what happens for the various scattering quantities in ADS when you go to flat space and vice versa. So, in 1 minute, what would be an Haag-Ruelle ADS construction? The idea is that we will look at amplitudes in ADS. So if I were to explain very simply how we define amplitudes in ADS, we just look at the conformal structure on the boundary. We use conformal symmetric to expand it like this. Okay, UC and BC are my conformal cross ratios. And then you can define out of this what we call conformal Mandelstam variables or just Mandelstam variables, so these. And then if you decompose G of ST and U, which is G of UC and PC, so the 4-point function up to the usual normalization, or usual prefactor, rather than normalization. If you decompose this, you can recognize the decomposition of generalized free field, which is essentially the identity, some contact term, which is essentially momentum conservation, and some connected part normalized by the contact term, which is essentially T. Okay, and this in the flat space limit, this prescription should give you the S matrix. There's a wonderful paper about that, and it's not just wonderful because my advisor wrote it. It really is wonderful. It's called PFT in ADS instead of LLZ. So I encourage you to read that paper. It's not too long and it's very well explained. So how do you do to take the flat space limit? Well, essentially, you use this relation I've just put here, and you say that the flat space is taking my dimensions going to infinity. Diagrammatically, if you want a very rough sketch, but visually it gives, I think, a very good intuition of what's happening. Take the Witten diagrams, take R going to infinity, just remove the circle that's around the Witten diagram. That gives you Feynman diagrams. That's, yeah, I agree, that's very hand-wavy way of saying things, but I think it sort of gives you an idea. And so in order to perform an ADS Haag-Ruelle, what we are working on is essentially using the flat space and the conformal field theory as a compass to guide ourselves in what we should do, because even to begin with, Wightman is a flat space story, so you have to be a bit careful. And then you realize that actually it will be a bit more involved because now you have to make evolution not just in some real time, but in a complex time as well. And so I think that's a good way to convince you that the take-home message number 3 still applies, which is that we still have lessons to learn from that Haag-Ruelle construction. And so we are quite happy to have it laid out in the flat space.
So, but this is the goal now. I lost. So
yeah.
There you gave a definition of what you mean by an amplitude.
Yes, exactly. So
now what do you need? Why do you need an Haag-Ruelle for ADS?
Oh, well, I would tell you, you can ask the same question about flat space, right? I already know out of quantum field theory, quantum field theory 1, what an amplitude is. Why would I need a definition?
No, but I mean, you can argue that's not well defined, right? Because it's not within the Wightman axiom.
Yeah, that's
whereas there you do have an axiomatic system for CFTs, and you're giving an axiomatic. I mean, you're giving an amplitude definition with an amplitude.
Yeah, but I was still a bit rough in how in about like what these limits mean and everything. So you have some mathematical control. You not have yet full mathematical control. I think maybe that's one way to answer your question.
So just understand, the goal is to have an independent definition of what.
Yeah, the goal is to really have an intrinsic definition at the end of the day.
Which is independent from the left, or is it?
Which at least should correspond to the results on the left if the results on the left converge properly in when R goes to infinity. Because of course we also want to recover a lot of scattering quantities like dispersion relations and such from ADS to flat space. Actually, the main things I'm interested in is I told you about this flat space story that tells you that the S matrix exists. Then we can play all sorts of analyticity games in flat space. This was done as well in the past century, mostly for D equals 4. So it would be nice to have it in any dimensions and know what breaks at which dimensions. And then the idea would be to replay the same game for ADS. And in particular, if you've heard about the Pochart bound in flat space, it would be very nice to have an ADS Pochart bound essentially that holds at finite radius, and to see what happens when R goes to infinity. Okay, you'd expect that you get the same thing, but like for example, the status of the optimality of the Pochart bound is not solved entirely. It's just not solved. And there were attempts, for example, there were papers by Kupsch, but it doesn't work. So it still is open. So maybe you're going to find the same thing, or maybe you're going to find something better. Some people argue that there should be a log S correction to the Pochart bound, and because it's log, it's such a damped function, if that's a word in English. It's such a damped function that you cannot really see it. And to give an outlook, I already gave only my future directions. I'm just going to give you back the beginning of the talk, so that it's full circle, and also to convince you that when I told you in the first 5 minutes I would have covered the entirety of the talk, well, it was true. So thank you for your attention for the next 50.
Thank you for the talk. One quick question before.
So it was not clear to me given that you have this Haag-Ruelle, why do you still need LSZ?
I don't know what you mean by need, but there's sort of the main motivation was to check that the quantity that we produced indeed is compatible with LSZ.
Why do you need to check that it's compatible? Why can't you just use this method to compute scattering amplitude? You said it's not computable, whatever. You had some negative comment about this. That this is not computable, we need LSZ. Why is it not computable?
Okay, then I agree the question. It's a fair question. Let me put it some other way. Indeed, you might say, let's compute it that way, but it's very much not convenient. And
why not? Can you explain why it's not convenient?
I would have a sociological rather than mathematical or physical answer to that, which is that most people, have worked with LSZ formalism so far. So if we show up with an S matrix and we say, oh, that's another S matrix, it's a natural question to ask, is it the same thing that we do with LSZ? That's the main motivation we had. And so hence the computability with the usual LSZ story.
You proved still. Have you tried to compute an S matrix using this formalism? Maybe it's very convenient. Before you try,
I haven't tried myself, but then it is okay. Then I have a last slide, which I think is perfect to answer your question. So it's a comment by Wightman, which is a bit of a witticism. And he said that cynical observers have compared axiomatic probability theories to some religious sects that build solid barns and lead celibate lives, a non-scientific equivalent of proving rigorous theorems and calculating no cross-sections. Basing myself on that wisdom by my elders, I know that I will not attempt myself. So no, to be honest, I have not tried computing an S matrix using this route. To me, it was really an existence route, proving that things are well defined, and then because they're compatible with LSZ, all the things I know how to do with LSZ, I can do with that quantity, which also is it helps me sleep at night to know that this quantity we computed is compatible with LSZ. Because if it was not, we would have a major problem, right? And we don't have a major problem.
So let's thank our speaker again.